Hello, you're listening to Naked Neuroscience, the podcast exploring the workings of the brain and the nervous system in our bodies and beyond. I'm Katie Haylor, and this month
we have simple synchrony exercises or ways of inducing synchrony with our participants, and even with strangers they tend to form a relatively tight and almost instant bond. They change the way they think about each other, they like each other more, they remember each other more, as if we've formed a long-term relationship with them.
we're musing what happens in the mind when we move. Coming up, what's going on in the brain that allows us to move? How might control over our movements change as we age? And is there more to being in sync with someone than you think? Plus, we'll be taking a stroll through the latest neuroscience news with the help of local experts. Let's tuck into some tasty neuroscience news morsels with perceptual psychologist Helen Keyes from Anglia Ruskin University and Cambridge University cognitive neuroscientist Duncan Astle. First up, Helen talked about a paper looking at how the degree to which we take risks may fluctuate a little more than we think.
I've been looking at a paper asking why it is that sometimes we make risky decisions, whereas sometimes we might be more risk averse. And this study suggests that perhaps we're not quite as stable as we might think we are. And while it might be true that we might have some risk-taking traits or some risk-averse traits, this study does show that actually our behaviour is quite erratic, more erratic than we might like to believe about ourselves. So the background of this is we tend to look at risk-taking at a population level, in that some people are prone to taking risks. In particular, younger people are known to be more prone to taking risks than older people by about 5%. The study is run on the basis that we are almost slaves to the brain chemical dopamine. So dopamine is a feel-good chemical in your brain, and generally people whose brains are saturated with dopamine will take more risks. This is really widely established. And in general, a big hit of dopamine feels good and people can tend to return for another rush. It can lead to a lot of addictive behaviours. In this study, the researchers used fMRI, which can show us different levels of activity in the brain over a period of time. And they focused on the dopaminergic midbrain. This is part of your brain that's really centrally involved in decision making. What was really neat about this study was that they tied the presentation of stimulus to your brain responses. So they looked at the dopaminergic midbrain, and if you were just in your resting state, had very low activity there, this would trigger the presentation of the stimulus.
And this stimulus is doing something risky?
It is indeed. So the interesting part is they tied the presentation of a stimulus to when you in your resting state had low or high activity in this region. And when that happened, let's say you had low resting activity in this region, you would then be presented with an interesting, potentially risky choice. So you would be asked to choose on a gambling task as to whether you wanted to go for a low amount of money, a safe option, so say £3, or gamble where you could get more money than that, so potentially £6 or £9, or 0. And they found that if in your dopaminergic midbrain you had very low activity, a low resting state, and you're suddenly presented with this gambling choice, there's quite a spike in your dopamine activity. And that spike in dopamine leads to you actually taking a more risky decision. So within the same session, if in your resting state, if you had a high activity in this brain area and you're presented with a risky choice, there wasn't quite the same dopamine spike, and you tended to make a safer choice.
Ah, okay. But this is within one person, right? So does that mean on any given day you can have higher or lower levels of dopamine in your brain?
It absolutely does. And this is what was quite surprising about this study. It was really neat. Just within one fMRI session, people were making quite different gambling choices just on things we have no control over. So background fluctuations in resting state activity in this part of your brain.
Here's me thinking that I'm a very habitually cautious person. Maybe that's not true.
Well, you may generally be a habitually cautious person, but I think you mightn't be as consistent within yourself as you might think. We need to remember that risk-taking activity isn't just a generic negative. There can be real reasons for us taking risks. So if we want to be ambitious and make progress, whether that's in our work life or our romantic life or any aspect of our life, we're going to need to have these fluctuations. We're going to need to sometimes push ourselves and take a few more risks. And this mechanism might be quite helpful for this. And indeed, the authors of this study suggest these background fluctuations might make us a bit more unpredictable and even might make us better able to adapt to different situations. So there could be good use in these background fluctuations. I think what this does point to is we can be a bit more self-aware. So it does suggest that some decisions we're making or the way we make decisions can be somewhat out of our control. Our behaviour can be somewhat erratic. It doesn't give us much hope, does it, for ourselves? But what it does suggest is that things that I'm quite interested in, like the development of driverless cars, that could be really, really good, because if these background fluctuations are going to affect particularly our risk-taking behaviour, let's take that out of the equation altogether and make more sensible choices.
Interesting. Duncan, you're sitting there very quietly. What are your thoughts?
It's interesting that there are various conditions where risk-taking can become pathological. So, for instance, people who become addicted to dangerous narcotics and that kind of thing. And there's been a lot of interest in the role that the dopamine system plays. And are there underlying genetic differences in our dopamine systems? Such that, for instance, if some people's dopamine systems are just much more erratic, then that means that there might be periods where they're exceptionally prone to taking big risks, like inject this substance.
Oh, I see. So there's fluctuation in everyone, but there could be more fluctuation in some people.
Yeah, so we know there is some genetic susceptibility for certain types of substance abuse addiction, for example. And it's interesting that there are various medications on the market to try and mimic dopamine action. So, for instance, something like Parkinson's, where because of the loss of dopamine receptors, the medication tries to boost the amount of dopamine. And what you'd find is exactly what you'd expect from what you've said, is that obviously helps with some symptoms, but they start to struggle with any tasks that require them to gauge rewards and make choices about rewards, i.e. make risks, because their levels of dopamine are just high the whole time.
Duncan there, and before him was Helen. Now, Duncan's been dipping into another study all about transcranial magnetic stimulation.
I found a very stimulating paper. Sorry, terrible puns. So it's using...
We love puns in The Naked Scientist. You know that.
It's good. Well, this is a good one. So this is using transcranial magnetic stimulation. It's also a very interesting paper. And it's looking at anhedonia, inability to find joy and enjoyment in the things that we do.
Are you talking about depression?
It is a very common symptom. About 70% of those with major depressive disorder will experience this symptom. It's regarded as a very stubborn symptom for treatment options. And people who score particularly highly on this symptom tend to be those who are most resistant to the current forms of treatment. So in this study, they recruited 19 subjects who all had major depressive disorder and particular problems with anhedonia. They rated them on an anhedonia scale, and they also performed a task that requires them to look at faces that convey different types of emotion. And those faces are manipulated to make it really tricky to judge the differences. How happy is this person? Then the subjects are divided into two groups, and both of them receive a type of stimulation applied to a part of the frontal lobe called the dorsolateral prefrontal cortex, which people have previously thought might be important in the symptom of anhedonia.
What does it mean to stimulate this bit of the brain? What are you doing to somebody?
So you will remember from GCSE or equivalent physics that wherever you get an electrical current running in a particular direction, you will also get a magnetic field running counter to it. It's called the right-hand rule.
This does bring back some memories of my physics lessons. Yes.
You're kind of coming out in a cold sweat.
I love physics at school.
Physics is fun. The same is true of your brain. So when the neurons fire, the axons in different layers of the brain are really well aligned, and that can create an electrical current that generates a magnetic field, and we can measure that outside the brain. And the same thing goes in reverse. If we can induce a big magnetic field just outside your head, then we can kind of fire the electrical activity within those neurons. And so what TMS does, it's two coils, essentially a big loop of iron that has got lots of wire wrapped around it. And then at the flick of a switch, a very large electrical current is put through the wire to create an electromagnet. And then when that's applied to the outside of your head, it generates a big enough magnetic field on the outside to get the neurons firing on the inside.
So how does this relate to anhedonia then?
Good question. So what they did essentially was to apply repetitive transcranial magnetic stimulation to this part of the brain called the dorsolateral prefrontal cortex. And they did it for 20 sessions. And in each session, a person would receive 3,000 bursts of TMS. And it's at 10 hertz, so 10 per second. And then people come back into the lab, they repeat the emotional faces task, and they repeat their anhedonia questionnaire. Now, half of the group, unbeknownst to them, they are not receiving the real stimulation. And what they find is that people who have had the real deal active stimulation do indeed show better sensitivity on that faces task. And the degree of change on the faces task is predictive of the degree of improvement that they show on the anhedonia questionnaire.
So what's going on then to make this relationship? Do we know?
Well, one popular idea is that there are various parts of the brain, which is something called the limbic system, so areas like the amygdala, that are really important in processing emotional content, but that can be regulated by other areas like the dorsolateral prefrontal cortex. And that what might be going wrong in subjects who experience anhedonia is they're not able to regulate this lower level brain area. And so one possibility is that by stimulating the dorsolateral prefrontal cortex, it's then better able to regulate the amygdala, and thus you're better able to experience the emotional content of the faces and experience less anhedonia. This kind of thing is seen as a potential alternative route to treatment. So we know that the current best quality NHS gold standard treatment is effective for sort of 50 to 60% of individuals. And so treatments like this are seen as a possibility, but there are some real questions surrounding it. So number one is feasibility. So can we really scale this up? Secondly, how long does it last? Would the person keep having to come back in every couple of months for another set of sessions? Can you deliver it to people of all ages? Could you give this to an adolescent, for example, who's particularly prone to depression?
I'm assuming that this is a safe technology that doesn't seem to cause brain regions any harm.
Yeah, so there's no evidence whatsoever that this does any harm to the brain. These studies are relatively high risk to run, so they tend to be run on a small scale. So really, to see whether it's genuinely effective, you'd need to scale it up.
Duncan Astle. And if there's some neuroscience news you want us to look at, or you've got a question you'd like us to address, get in touch. You can email neuroscience@nakedscientists.com.
Hello, I'm Chris Barrow, bringing you a brand new podcast called Naked Gaming. This is where we look at gaming news.
If you have a hit, if you make a first game and it hits, it's incredibly hard to recreate that in the second game.
Reviews. Is it wrong to give a game 0 out of 10? That feels...
Oh, I love it. Go for it.
Okay, I'm just going to go hard in here. 0 out of 10. Don't waste your money. And we also go back in time with Retro Revival.
I think I'm a hypocrite because last time I'm like, oh, well, they just made the same game again and that's bad. But this time I'm like, nah, it's pretty good. I'm happy with that.
Make the same game.
Make it again.
Download it now wherever you get your podcasts.
Music in the programme is sponsored by Epidemic Sound, perfect music for audio and video productions. And this month on Naked Neuroscience, we are mulling over movement. First up, what's actually going on in the brain and body to allow us to say, hold a cup of coffee? Well, stick the kettle on, because trainee doctor Isabel Cochrane has been brewing up an answer.
Movement's generated when a type of nerve cell called a motor neuron sends a chemical signal directly to a muscle, causing it to contract. This process can be voluntary, allowing us to do things like typing or throwing a ball. Or alternatively, movements can occur in response to a sensory stimulus from the environment. Contact with a hot surface or a stinging nettle, for instance, causes, ouch, a rapid withdrawal reflex. The parts of the nervous system that generate movements are collectively called the motor system. Over millennia, these have evolved to operate automatically. This means that most of our movements are not under direct conscious control. even though the decision to carry out a particular movement might be conscious, we do not have to think explicitly about the sequence of nerve signals, muscle contractions, and joint movements that are going to be needed to carry out an action successfully. These calculations are instead performed at various levels in the motor system. So let's start by looking at withdrawal reflexes. These occur when a painful or unpleasant stimulus is experienced, for instance, touching a piping hot oven dish. The result of this stimulus will be something we have all experienced, an almost instantaneous removal of the affected digit from the offending item. When researchers first studied this historically, they realised that the reaction occurs far too rapidly for the movement commands to be going via the brain. Instead, sensory neurons that detect painful stimuli are linked, via short spinal nerve cells called interneurons, straight to the motor neurons responsible for withdrawing a limb from the noxious stimulus. In other words, the machinery of the spinal cord is sufficient to generate this basic goal-directed movement. Of course, we know the story is not so simple. For instance, no matter how painful it is, we can resist dropping our favourite mug, even if it's full of steaming coffee. Many of our spinal reflexes are ultimately still under the control of the brain, which can refuse permission for a particular action to take place. So, is the spinal cord able to generate movement other than reflexes? In vertebrates, it would appear that the answer is generally yes. The spine contains networks of neurons known as central pattern generators. These fire rhythmically to produce stereotype movements such as swimming, scratching, and walking. However, the story is less clear-cut in man. Scientists aren't sure whether there are central pattern generators in the adult human spinal cord, or whether these circuits are located elsewhere in the nervous system, such as the brain. The part of the brain that is responsible for producing movement commands is called the primary motor cortex. This is a strip of brain tissue which sits roughly beneath where your headphones would rest on your head. The primary motor cortex is organised like a map of the body, with different regions of the cortex responsible for muscles of a particular part of the body. This part of the brain, and the bundles of nerve fibres that flow from it, are commonly affected by strokes, which is why one of the most prominent symptoms of a stroke is paralysis of the arm, leg, or face. And based on which of these structures is paralysed, one can predict quite accurately which part of the motor cortex has been affected. The nerve fibres that flow away from the motor cortex form two bundles that run down the front of the spinal cord. These are called the corticospinal tracts. The nerves exit these bundles at the right locations along the spinal cord to connect to and activate target motor neurons and intermediate interneurons that control muscles. So, how does the motor cortex actually make a movement happen? At a simple level, a nerve cell in the motor cortex becomes active and fires a barrage of impulses along its fibre down the corticospinal tract. These impulses are transmitted to and activate a select group of motor neurons and interneurons in the part of the spinal cord that controls the relevant part of the body you want to move. When the motor neurons fire up, the muscles they activate contract, and you move. In reality, it is of course more complex than this. The motor cortex tends to be organised in terms of motor synergies. This means that the brain contains libraries of various useful movement combinations. For example, activating the muscles that stretch the elbow and the muscles that stretch the wrist simultaneously in order to reach out and grab an object. Sensory feedback during a movement can help to modify these synergies, both at the time of the action, in order to refine the movement, but also in the future, enabling a learning process by which this library can be expanded. You might wonder, though, what controls the motor cortex? That role of planning and refining movements before they happen falls to structures that sit just in front of the motor cortex, right behind your forehead. These are the supplementary motor area and premotor cortex. They are richly connected with the front parts of the brain that are involved in decision-making, as well as with other brain structures, such as the cerebellum, which helps with the coordination of movement and in learning new sequences of movements, and the basal ganglia, which are involved in delivering the go signal that kicks off a movement in the first place. So, next time you reach for your cup of coffee, spare a thought also for the millions of neurons buzzing away in your motor cortex, cerebellum, and spinal cord to ensure the coffee ends up where it should and when it should.
Thanks, Isabel. I can appreciate my Americano in a whole new way. Now, Isabel mentioned there that the brain coordinates movement. But as we get older, this can start to change.
As people get older in their 60s, 70s and later, their movements become a bit jerky, less smooth, and that makes things as simple as making a cup of tea a bit more difficult.
That's Anne-Marie Valence from Murdoch University in Western Australia, who wants to know how the way our brains control movement may alter with age. To get a better idea of what's going on inside the brain, Anne-Marie uses a technique called transcranial magnetic stimulation, just like Duncan mentioned earlier, to probe the activity of parts of the brain involved in movement control. Chris Smith found out more.
We use a non-invasive brain stimulation technique called transcranial magnetic stimulation. And this is a reasonably new technique that allows us to activate the brain cells non-invasively in a comfortable and safe manner. And the technique relies on electromagnetic induction because we know that brain cells are activated through changes in electrical activity. So we can use transcranial magnetic stimulation to induce a magnetic field that passes through the scalp, which induces electrical current flow in the brain cells and activates them.
And does it turn the cells on, or does it turn them off, or both?
It can do both. It turns the cells on. So if we give a large stimulus, then we can get an excitatory response, or we can see the effect of activating those brain cells. We can also use it to disrupt brain cells. And so if someone is performing a movement, in this case, and we give a big stimulus to the part of the brain controlling that movement, it can temporarily, in the order of milliseconds, disrupt that activity.
And how do you focus where that effect happens?
Well, part of that comes down to the design of the coil that we use to stimulate. It's in the shape of an 8, which I'm sure you can imagine, and the middle of that coil is where the maximum stimulus is delivered. So that allows us to give a fairly focal stimulus, and when we are deciding which part of the brain that we're interested in terms of movement, we're interested in the primary motor cortex, and this is a strip of brain that runs pretty much from your ear to ear. So if we hold our coil over that motor cortex or the motor strip, deliver a pulse, we can see the effect in the muscles of the body that we're targeting.
But you measure the muscle activity electrically, so you can see what the muscles are doing when you do this change in what the motor cortex is doing, so you can see how one is influencing the other.
Exactly. So in a typical experiment, we would put some recording electrodes over small muscles of the hand, for example. We would then use our coil to stimulate the representation of those hand muscles in the motor cortex, and after a very short latency, we can see the twitch in the muscle recorded, as you say, with electrical activity.
And how does this help you to solve the problem that you set out asking, which is how movements get initially planned, then executed smoothly, and why they fall apart a bit as we get older?
We can use this technique to measure how active or how excitable particular parts of the motor cortex are. And so if we compare the excitability of particular regions between younger and older adults, we can start to understand how the brain is functioning in these two age groups and whether there is some age-related decline in brain function, and that might be associated with the age-related decline in movement control.
And is that what you're finding?
Yes. So one recent study that we've conducted is actually looking at connections between two motor areas of the brain, the motor cortex and the supplementary motor area. Now, this is a brain area that's a few centimetres in front of the motor cortex, and it's important for bilateral movement, so controlling both of the limbs, both of the hands in a coordinated manner. When we probe the connections between the supplementary motor area and the motor cortex with transcranial magnetic stimulation, this connectivity is weaker in older adults than younger adults, and the strength of that connectivity is actually associated with how well they can perform a bilateral task, like using the hands to make a cup of tea or open a jar.
Do you have any insights as to why you're seeing that? And could you, for instance, go to a brain bank and look at physical brain specimens to see if in people who have obviously now died but would have had these sorts of symptoms, whether you can see any anatomical reason for why you see this functional change?
Yeah, it's a really interesting question, and we're interested in looking at the brain structure. We know that as people age, there are structural declines in the brain, and we know that this structural decline occurs in motor areas like the ones I've described. The structural decline tends to happen before we notice these symptoms in movement, the poorer movement. So it would be really interesting for us in an alive person to actually measure the structure of these connections by looking at what we call the white matter tracts and seeing whether they can predict a decline in movement control and whether we can also measure the functional decline and its association with movement control.
And it's one thing to identify why something's happening. It's another to try and do something about it. Do you think this is going to give you any insights into how we can help people either not decline so much at all in the first place, or if they are at risk of this happening, help them to improve their function in some way so they don't end up too shaky to write a cheque or make a cup of tea?
Yeah, that's the overall goal actually, and I think we can do that. Two potential approaches to that. The first is actually to use the technique I've described already, transcranial magnetic stimulation, in a repetitive fashion. Instead of giving one pulse at a time to measure its effect on the brain, we can give hundreds of pulses over the course of several minutes, and that has been shown already in a healthy young brain to increase the excitability of the stimulated brain regions. So the plan to test actually is whether we can repeatedly stimulate the supplementary motor area and the motor cortex and see whether that can, in the short term, improve movement. If that is the case, then that could be a potential therapy, repetitive brain stimulation. The second approach, which might be more widely available, is to test interventions that we think will improve movement control and go in and probe functional connectivity. And then we have an evidence-based intervention to improve movement control.
Have you got a study population you can look at? Is there anyone who's willing to take part in these sorts of studies?
Yeah, we actually run a lot of studies here at Murdoch University. We're recruiting older adults from the local community, and they're very happy to participate, actually.
So what, you got an old folks home next door?
Actually, we do. But we also target the local community centres, libraries, sporting clubs, and we have really good engagement with the ageing community, and we feed back to them the results of our studies and have morning teas and catch-ups like that, which they really enjoy.
Anne-Marie Valence there from Murdoch University. Now, have you ever heard the phrase, to walk a mile in someone's shoes? The idea is to spend time trying to understand someone's point of view before judging them. But it turns out that this phrase could be more than just a metaphor. Being physically in step with another person, in other words, in sync, can have an impact on your social relationship. This is according to Lyndon Miles over at the University of Western Australia, who has been studying this synchrony for some time. I took a proverbial stroll with Lyndon to try and get to the bottom of being in sync.
So the idea of synchrony is that we move at the same time with the same movements as somebody else, with their interaction partners.
Say I'm walking down the street with a friend or a relative or maybe someone I don't know. I strike up a conversation and I find myself hitting the pavement with my feet actually at the same time that they're doing so.
That's exactly right. That's what we'd call in-phase synchrony, and your footsteps tend to coordinate in the same way, almost as if you're marching together with them, but often it just happens spontaneously and unintentionally and you don't really even notice that it's going on. A lot of the time, particularly the things we do for fun, like singing and dancing and moving, we'll practice really quite a lot at synchronizing our movements. And we tend to get the same sort of positive social benefits there. We enjoy our moving together with other people. We pay lots of attention to it. We get a lot of social feedback when we do the same thing as somebody else. It tends to be that regardless of whether it's spontaneous or intentional, we still enjoy the benefits of synchronous movement.
I remember being a kid and being stuck in the back of the car on a long car journey and noticing that when you're in a traffic jam, car indicators are sometimes in sync and sometimes out of sync, and it's really annoying when they're out of sync. But I also noticed that I used to do this with my friends. I would purposely try and be in step with them, Does that have any relevance here if we're talking about social relationships?
That's really funny because I had the same problem as a kid. I got quite annoyed when the indicators were out of sync with each other. That's what we'd call incidental synchrony. There's no real coupling between the car indicators. They come and go, or they just kind of coincidentally synchronize. What's really important with people is that we have some sort of coupling or some sort of joining to them. Often it's just paying attention to them, seeing their movements, and their movements influence ours, and vice versa. Our movements influence theirs, until we come to a kind of a common movement frequency and we do the same thing at the same time.
So you've got mathematical with this relationship, right? Can you tell us a bit about how that works?
What we really do is just borrow some models from physics. They essentially say that as long as two things are moving at roughly the same frequency, so the same speed as each other, and somehow they're joined, so they're coupled in some way, often visually with people, or we could hear their footsteps, then the models predict that will coordinate in either an in-phase coordination, so we're stepping at exactly the same time as the other person, or an anti-phase coordination, so that, for instance, when we're stepping with our left leg, they'll be stepping with their right leg. And the models predict this across all sorts of systems, from metronomes synchronizing to fireflies flashing off and on to people coordinating their footsteps.
So what has that got to do with our social relationships then?
Turns out that when we synchronize in this way, because there's an infinite number of ways we could coordinate our behavior, people tend to coordinate in exactly the same ways it's predicted by the physics. And that seems to be a sign of positive and effective social relationships. So we like each other more when we synchronize, we remember each other more, we get a wee boost in self-esteem.
And how strong is this relationship between socializing and being in step, literally?
Well, I guess there's a whole bunch of different things and different influences of how well we get along with each other. We almost always use strangers coming into the lab, and we have simple synchrony exercises or ways of inducing synchrony with our participants. And even with strangers, they tend to form a relatively tight and almost instant bond. They change the way they think about each other, they like each other more, they remember each other more. Typically we remember more about ourselves than we would remember about other people, unless they're significant others. But after about a 2 or 3 minute period of in-phase synchrony, we start to remember more about our interaction partners, as if we've formed a long-term relationship with them. Our cognition or our social cognitions change in the same way they would when we've had a long-term and substantial relationship with somebody. They engage in more in-depth conversations and that sort of thing. And it's an interesting relationship because it kind of goes both ways. The more we synchronize with people, the more we like them. And the more we like people, the more we synchronize with them.
How have you discovered that the social cognitions changed? Are you sticking people in a scanner or are you asking them about it?
So we do simple things like we give them a task where they're moving synchronously or asynchronously, and over headphones we play them some words and ask them to say those words out loud. They believe that these words are just distraction words, and so they're saying some words out loud, they're hearing an interaction partner saying some words out loud, and after 2 or 3 minutes of synchrony, then we stop them and we give them what we call a surprise recall test. And after they've been synchronous, they remember just as many words that they've said as their partners said. But after an asynchronous interaction, or they don't have a movement involved in the interaction, they tend to remember more about themselves than the other person. This is what's called the self-reference effect. It's a really common effect. I remember more about myself than other people, and we can accept for when those other people are significant others, and we can kind of replicate that long-term relationship with a 2 to 3 minute period of synchrony. We also remember what these people look like better, so we take a photograph of our participants and then we morph their faces with a whole lot of other faces, so they end up seeing people who look similar to each other, and our participants who have synchronized with an experimenter tend to be able to pick who the experimenter is out of that bunch of faces much better than people who haven't synchronized.
Is there any breakdown of particular social relationships? I'm wondering if this might be quite a good dating technique. Walking in step with people.
I guess it should reinforce the initial liking between each other. We have a little bit of data that we haven't published yet that says friends probably don't coordinate or synchronize to the same extent as strangers. And we're wondering whether this is because we have this kind of deep desire or need to belong and need to affiliate with people and need to have smooth social interactions. So we deploy coordination as a mechanism to overcome any social awkwardness and kind of close the gap between people, particularly on their initial meetings.
I'm really interested to know how long we've known about this, because people have been using this technique for hundreds of, maybe even thousands of years, getting armies to march together and the social impact that must have. I mean, that's got to have gone back centuries, right?
That's right. I think we've been implicitly understanding that something about doing the same thing at the same time as each other is a really strong form of social bonding. So there's some ideas that this has a deep evolutionary history, and this is one of the first ways we were able to form groups and coalitions together by perhaps singing or dancing or drumming around the campfire. And as you say, military have used this for a very long time. The really interesting thing is military still use a lot of marching drills. They don't march into battle anymore. Isn't so wise with the invention of the machine gun and things along those lines, but military drill still involves a lot of marching in time and behaving in the same way of somebody else. And the idea is it provides a cohesive unit, it provides, a sense of belonging and a sense of camaraderie with your fellow people.
Can you tell us a bit about why you think this relationship occurs? What's the mechanism that you think you're getting at here?
Probably a multi-layered mechanism. I think doing the same thing at the same time has a lot of reinforcing properties. So we're sharing a common interest, we're sharing a common fate. It also means that we're paying attention to each other. Part of the way that we synchronize is by having an attentional coupling, by knowing what other people are doing and seeing what other people are doing. And this is also a sign of a good interaction or a good relationship. We pay lots of attention to the people we like. And so it's mutually reinforcing in this way. A wee bit lower in the system, in the brain level, we get common patterns of brain activity when people are doing stuff. So again, they're sharing experiences. It tends to be, again, mutually reinforcing. There's some evidence that there's some hormonal changes. So we may have an endorphin release, a pleasure hormone when we synchronize with other people. And so I think there's a lot of levels which all seem to reinforce the same idea that doing the same thing as our interaction partners provides a platform or a basis for an effective and pleasant social interaction.
So actually, me skipping down the road with my friends when I was little, linking arms and trying to step at the same time, seems to make quite a lot of sense.
I think it's one nice way of building up some enduring bonds.
This relationship, if it is quite a strong one, could this be used as an indicator of when, for instance, someone might be having social difficulties?
Yeah, absolutely. Some really recent work we've been doing is looking at social anxiety. So people who experience symptoms of social anxiety tend to have accompanying social difficulties. And what we've been showing is that the way people who have higher levels of social anxiety coordinate with other people has less stability. So the coordination's less good, it's less stable, it doesn't happen in quite the same way. And we're starting to wonder whether this has a wee bit of a feedback loop. So if symptoms of social anxiety are producing less effective coordination, perhaps that then heightens the sensation or the experience of social anxiety, which again, in turn, lessens the quality of coordination. So we're starting to do some work that looks at whether symptoms of mental health and whether deficits or disruptions to coordination can act as a marker or a signature of instability in mental health.
But it's not just stepping, is it? We've been talking a lot about walking here, but just thinking, I played the cello as a kid. There must be so much about synchrony and asynchrony when you're making music together, for instance.
Absolutely, and I think music gives people a common source or a common rhythm that they can, use to both synchronize together really easily. But I think also other movements like posture and postural sway and just all of the little non-verbal behaviors and movements that we have probably contribute to the same idea. Similar emotional experiences, and we mimic and synchronize each other's facial expressions and emotions as well, I think then feeds into the same idea that if we synchronize our behaviors, then that can lead to a shared and common understanding.
Lyndon Miles there from UWA. So from the movement involved in holding a mug of coffee to technology that may one day help us to turn down or at least better understand the tremors that can trouble us as we age, to how being in sync with someone might just be the start of a beautiful friendship. That's all on the neuroscience of moving for this month. Thank you to everyone involved in the show: Lyndon Miles, Anne-Marie Valence, Isabel Cochrane, Duncan Astle and Helen Keyes. And thanks to you for listening to the show. We'll be back next time with more Naked Neuroscience. If you've got any feedback, drop us a line. It's neuroscience@nakedscientist.com. I've been Katie Haylor from the Naked Scientist team. Until next time, goodbye.